start talking. Okay, so this is problem number 5, chapter 16. And what it says is we have a set of accelerating plates. Basically, they're parallel plates, but they have a hole in them. So we would have something like this. And then we'd have another set. So let me just group those together and clone them. And so what we would have, if we had electrons, we would want them to be, these would be the positively charged plates. And these would be the negatively charged plates. And we have like a little electron there. And so the electron, once it got to this point, it would be repelled by the positive charges and attracted by the negative charges, and that would create a force which would cause that thing to accelerate. And it says the potential difference. So we have, let's say, V positive and V negative. The potential difference is the difference between those two. So delta V is 25 kilovolts, which is kilo is 1,000, so it's 25,000 volts. So you can measure that with a voltmeter if you have the right kind of voltmeter. And it says the distance between the plates is 1.5 centimeters. So D equals 1.5 centimeters, which will convert to meters immediately. So it's 0.015 meters. And so what happens is that there's a relationship between voltage and electric field and distance. And basically it says that the change in voltage is equal to the electric field times delta X, the distance it's traveled. And if we remember, voltage is potential energy divided by unit charge. So if we multiply by Q, our charge, we would get change in potential energy is the electric field times the charge, which is a force, times delta X, which is a distance. Force times distance is work. So that's where all this comes from. But as far as solving this problem, that's the only relationship we need. So if we have a constant electric field, and we will have an electric field, let's draw those. We have electric field lines which are going from positive to negative. So that's those are just some of the electric field lines going that direction. Okay, so we have a constant electric field. It means the electric field is the same here as here. It's all the way through. It's in one direction. So if we have a constant electric field, then we know that the voltage is related to that value of the electric field divided by delta X. So if you had a certain electric field and you made the distance smaller, then if you had the same voltage, then the electric field would be higher as well. Because as it gets smaller, that has to get higher to maintain the same voltage. Okay, anyway, the question says if the distance between plates is 1.5 centimeters, find the magnitude of the uniform electric field. So all we have to do is solve this. E is equal to the change in voltage divided by delta X. And our voltage is 25,000 volts. And we divide by 0.015 meters. And therefore the electric field, to make that happen, is going to be equal to, get my calculator out. So we get 25,000 divided by 0.15, which is equal to 101.67 times 10 to the 6th power. And that's volts per meter. And I think it's also newtons per coulomb. That's the typical way of measuring electric field is newtons per coulomb, force per unit charge. So they're exactly the same. Okay, so that's it. That was pretty easy, huh? Okay, problem number 7. This is chapter 16, page 565. And so it's very similar to what we just did in problem 5 if you're doing that one, if you just done that one. In this case, we have parallel plates, so we don't have a hole in them. We just have the plates. Okay, this is oppositely charged plates. That means we have positive charges on one side. We have negative charges on the other side. Okay, and it says there's a potential difference, delta voltage, of 600 volts. And this is the high voltage side, and this is the lower voltage side. And we can tell that because if we took a test charge here that's positive, so going to put a little test charge, what would normally happen is we would get pushed away from this side and drawn towards this side. So it would tend to want to move downward, which is like something that falls. You decrease the potential energy. So to move it from here to here, we have to increase the potential energy. And therefore the voltage increases as we go from one side to the other. Okay, and the distance between the plates is, between the plates is 5.33 millimeters. So called D, 5.33 millimeters, which we will convert to meters, but it says 0.00533 meters. Sorry, that's so small. Okay. What is the magnitude of the electric field between the plates? So just like previously, the voltage is equal to the electric field times D. And so the electric field is just equal to the potential difference, or the change in voltage, divided by the distance. So let's move this over to the left just a little bit so I have some place to put my stuff in. So we have 600 volts divided by the distance, which is 0.00533 meters. So 600 divided by 0.00533. So we get 1.12 times 10 to the 5th volts per meter, which is also newtons per coulomb. Okay, so that's part A. That was as easy as it gets. Okay, B. What is the magnitude of the force on an electron between the plates? So we draw a little positive particle up here. Let's draw a little negative particle and put it inside there and think about what's happening to it. So here's the particle. We'll put a negative sign in it, and then we'll group them together. So so here's the negative particle. And the electric field lines are going to be going in this direction. So positive particles go with the electric field lines. Negative particles go against them. So it's going to go in that direction. Start here, and then it'll go in that direction. So the force acting on that, remember, electric field is also defined as force per charge. And we have an electron, so we know what the charge of an electron is. It's 1.6 times 10 to the minus 19th, I'm pretty sure, as far as the charge is concerned. And here it is, page 501. So the charge is 1.60 times 10 to the minus 19th coulombs. remember, this is also coulombs per Newton per coulomb. So we know the electric field. Let's just go ahead and write it down. 1.12 times 10 to the minus, or 10 to the fifth newtons per coulomb. So the force is just going to be equal to the electric field times the charge. And the electric field is 1.12 times 10 to the minus, or I keep doing minus here, I don't know what my problem is. Okay, 10 to the fifth newtons per coulomb times the charge, which is, and I'm just going to use the magnitude. We can infer the direction. It's easier to do that than worry about signs and stuff. So 1.12 e to the fifth times 1.6 e to the negative 19. So the force is pretty small. It's I'm going to round off, well, 1.79 times 10 to the minus 15th newtons. And the force, let's go back to the top. The force is going to be in the direction, opposite the direction of electric field. So it's going to be pointing upward in the y direction. Okay, and then the final part of this problem, if I can find it. How much work must be done on the electron to move it to the negative plate if it is initially positioned 2.9 millimeters from the positive plate? So here it is, and if this distance, so let's put this over here. So if our initial distance is that, so it's 2.90, so this is 2.9. Therefore, the distance we must move it from here to here is going to be the difference between the two. So let's put another screen up. So the distance, the delta x that we're going to move is just 5.33 minus 2.90. 0.33 minus 2.90 is 2.43 millimeters. Convert that to meters, so we get 0.00243 meters. So that's delta x. And that's the force, and that's the distance. So the work is just equal to force times distance. And our force is shown right down here. So we have 1.79 times 10 to the minus 15th newtons multiplied by the distance, 0.00243 meters. e to the negative 15th times that distance. And so the work is going to be equal to 4.35 times 10 to the minus 15th Newton meters. And a Newton meter is a joule. Okay, just checking my answers here. Okay, I'm in good shape. So that's the amount of work done. And so we go back to the picture on the previous page. As we move the electron from here to here, we're going to move a distance of 2.43 millimeters. And because this is pushing against the force is pushing it up. So because I'm actually having to provide a force to move it in this direction. The other case, the force is caused by the difference in the potential. It goes that direction. If I just let go of it, it would quickly go to the positive plate and get attracted. But if I'm pushing it backwards this direction, I'm increasing the voltage of the particle, and I'm also doing work on that particle as I do that. Okay, what we're going to do is problem number 13 in chapter 16. And so let's make a drawing. We're looking at the voltage at a particular point, and we have 4 points involved on a corner. So let me clone these here. So these are the charges associated with the different parts, and we're trying to find out what the charge is, or what the voltage is at this point. So it's on the other end of this rectangle. So let's do those distances. Those are given. And let's see what they are. So this is 6 centimeters. This is 3 centimeters. This charge is positive 8.00 microcoulombs. Here we have positive 2.0 microcoulombs and another positive 4.0 microcoulombs. Okay, so the first part is we do it this way, and then the third part, the second way, is we replace one with a negative charge. So this distance is just, you're going to use the Pythagorean theorem to find the distance between that charge and the point of interest. So let's call this distance d. So d is equal to, hold on a second, d is going to be equal to the square root of 6 squared plus 3 squared. And so that's going to be 36 plus 9, which is 45. So we have the square root of 45, which is 9 times, I can't write 45 in here, 45. Okay, so 9 times 5 is 45, so it's going to be equal to 3 times the square root of 5. Okay, so that's the distance, so that's centimeters. So the expression for voltage, and these are all going to give us positive voltages because we have, just hold on a second, I'll make sure I'm doing the voice here. Okay, I'm good shape. Okay, so we go look in the book for the equation. I don't remember exactly what it is. And we find out that the voltage, this is the equation on page 538, equation 16.4. It says the voltage is equal to the constant, Coulomb's constant times charge divided by R. And so we can do this for each one of these charges. We just have 3 different distances. And then to find the total voltage here is just the sum of the 3 voltages. So let's add a second page. And let's label these. I don't think they label them in the book. So look if they've got numbers on them or not. Okay, so let's just number them. Let's call this is 1, this is 2, this is 3. So the voltage due to charge 1 is 8.99 times 10 to the 9th. That's the Coulomb's constant times the charge, which is 8 microcoulombs. So that's 10 to the minus 6. And we divide that by the distance, which is the distance from 1 to here is 6 centimeters. So that's going to be 0.06 meters. So let's plug that into the calculator. 8.99 e to the 9th times 8 e to the negative 6 divided by 0.06. So I get a big number, 1.20 times 10 to the 6 volts. Okay. I'm just going to stop the recording for just a second. Okay, I'll just make sure I was going on the right path, which I am. So we do the voltage associated with charge number 2. And so that's going to be 8.99 times 10 to the 9th. And our charge is 2.00 times 10 to the minus 6 coulombs. And we divide by that distance, which is going to be equal to 3 times the square root of 5. So put that in the calculator, 8.99 e to the 9th times 2 e to the negative 6 divided by 3 divided by the square root of 5. And, okay. It just doesn't seem right here. Okay, I'm just going to write it down. So this is 10 to the 3rd, that's 10 to the 6th. Oh, I need to divide by another 100. I need to, so that's in centimeters. I need to change that to meters. I knew there was an issue here. So let's multiply that by 100 times 100. Okay, that makes a little more sense. So here we've got 4.0 times 10 to the 5th volts. And that makes sense because this is 1/4 the amount. And this is going to be larger. So that should be, oh, I see I made a mistake again. Make sure I got that right. Okay. Yeah, I got to multiply by 2 and divide by 3. Okay, there we go. What I was noticing was it should be at least 1/4, and even more than 1/4, and it was actually the other way around, so I realized that let's transpose some numbers. So it's 2.7 times 10 to the 5th. Okay. So that's kind of what you do a lot of times is you go through these things and you're looking to see whether the numbers make sense just from a rough standpoint. So that's what I was doing. And so sorry to slow you down, but and so the distance between this point and point 3 is going to be 3 centimeters, which is going to be 0.03 meters. And so we get the voltage due to charge 3, 8.99 e to the 9th times 4 e to the negative 6 divided by 0.03. And so I get 1.19 times 10 to the 6th volts. So our total voltage at this point, the red point, is just going to be the sum of the 3. So the total voltage is 1.20 times 10 to the 6 volts plus 2.7 times 10 to the 5th volts plus 1.19 times 10 to the 6 volts. And if we add those up, 1.2 plus 10 to the 6 plus 2.7 times 10 to the 5th plus 1.19, I get 2.66 times 10 to the 6 volts. So that's what happens. That's the voltage at that red point. And they said, what happens if we change the charge to -2? Well, this one would become a negative. So part B, we have the same thing. The magnitudes are the same. What happens is that the sign changes. So we have that plus 2.7 times 10 to the 5th volts minus 1.19 times 10 to the 6 volts. So 1.2 plus And what I'm doing here is I'm changing that to 0.27 times 10 to the 6, so I can just add the numbers. So I'm just adding 1.2 plus 0.27 plus minus 1.19, and I get 0.28 volts. So let me just stop the recording for a second, and I'll check the answer and see if we're okay. Okay. Okay, I didn't read the problem correctly. This is the one that involves the 2 microcoulombs. So this is going to be negative, and that's going to be positive. So just have to correct this last little bit. So I'm taking 1.2 minus 0.27 plus 1.19. That gives me 2.12. So I get 2.12 volts. When I had the negative 2 microcoulombs, I replaced this one originally, but I wasn't paying attention. So this is the one that I changed to negative, so that becomes negative, and therefore the voltage is less than when everything was positive. So I think that's it. This is problem 17, chapter 16. This potential is a problem about electrical potential. And what we have are 3 charges shown by the circles. And this has a charge of Q, positive Q, and these 2 have charges of negative Q. And the value for Q is 7.00 nanocoulombs. And nano is 10 to the minus 9th, so it's 7 times 10 to the minus 9th coulombs. So what they're looking for is what is the electrical potential or the voltage at this point. It says calculate the electric potential at the midpoint of the base. So this is a base. This is a isosceles triangle, so these 2 lengths are the same. These 2 angles are the same. And so this is halfway in between. So we know the distance between here and here is going to be 1 centimeter. So let's go ahead and show that. Because what we need are the distances from the charges to the point in space. So let's move my 2 centimeters down just a little bit. Okay, so this is 1 centimeter. And we have to figure out what this distance is from here to the point. And so you just use the Pythagorean theorem. Let's go ahead and put another arrow in here. So what we're doing is looking for that distance. And you have a right triangle formed here. This is the hypotenuse. This lower side is going to be 1 centimeter. So let's call this D. And so D is going to be equal to the square root of 4 squared minus 1 squared. That's because this side squared plus that side squared equals that side squared. So if you solve for B and take the square root, you'll end up with this result. And that'll end up being the square root of 15 because 4 squared is 16 and 1 squared is 1, so 16 minus 1 is 15. So it's going to be the square root of 15 centimeters. Let's just go ahead and convert that to a decimal point. We're not doing calculus here, we're doing physics. So we just need the square root of 15, 3.87. Now we're going to have to convert these distances to meters when we do the calculation. We have already converted the charge to coulombs. And there's one way we could do each one of these separately, or we can kind of do somewhat of a shortcut in that we can just put them all together, because ultimately the voltage at a particular point is going to be the summation, meaning we add them all up together, of the Coulomb's constant times the charge. As long as we reflect the correct sign of the charge here, we'll be in good shape, divided by the radius. Is that right? Radius, yeah. Electric field is radius squared. Voltage is radius. So we're in good shape. If we had a question about that, we could go look at the back of the chapter, which has summaries, and it's just the radius. So in this case, our voltage is going to be, what do we got here? We got Coulomb's constant. Coulomb's constant is multiplied by everything. So let's just factor that out. 8.99 times 10 to the 9th. And Coulomb's constant is going to be, I'm trying to remember the units of that. If we go back and think about how this was originally derived, it was K sub E Q1 Q2 divided by R squared. So if the units of Coulomb's constant, you could figure out the unit of force would be newtons. We multiply by the units of radius, which are meters. We have that squared, and we divide by the charge. And so we would get newtons meters squared per Coulomb squared. So if you ever forgot it, if you go back to the fundamental definition. Okay, so that's going to be multiplied by this whole thing. And so what we do is we take the charge, and the radius doesn't have it's not a directional quantity, so it doesn't really matter. The voltage due to this charge is going to be the same as the voltage due to this charge, and we'll add them together. So we'll take negative 7.00 times 10 to the minus 9th, and that's going to be coulombs, divided by the radius, and that's 1 centimeter, but we need to convert that to meters, so it's 0.01 meters. Okay, so that's the discharge here. We have the same thing happening in the next charge. So this is all the same numbers from this charge. And then finally, the last charge will be the one that's positive, which is going to be positive 7.00 times 10 to the minus 9th coulombs. And the distance is 3.87. But we'll have to convert that to meters. So it's 0.387 meters. So if we now plug in 8.99 e to the 9th times the quantity, negative 7 e to the minus 9 divided by 0.01 minus 7 e to the minus 9 divided by 0.01 plus 7 e to the minus 9 divided by 0.0387, close the parentheses. And what we get is negative, the actual number is 10,959, but we'll round that off to 11,000. So there'd be 11,000 volts, and therefore we can say that's negative 11,000 kilovolts. And that's the answer. Okay, 127 is a capacitor problem. And capacitors are used for storing energy in electric circuits. And they consist of two plates. So I'm going to show two plates here. And they have a certain area. So if we were to draw this in 3 dimensions, we'd have this thing going out in this direction. So I'm just trying to draw a perspective drawing. So this would have a certain area, cross-sectional area, which would be dependent upon the width and the length of the plate. And the one on the plate on the bottom is the same dimensions. So that's the area. It has a distance between the two plates. So this distance here, we'll call that D. And so what happens is we use the circuit. So there's a circuit that goes around through here, and there's a battery. So we put a battery in here, some way of creating a difference in positive and negative charges on either side. So let's say this is the positive side. So you put all the you take electrons from here and they go through the circuit and they come out here. So we transfer electrons basically from this surface through the circuit to the other side. And that creates an electric field between the two plates. So there's an electric field that goes in the direction as shown. Goes from the positive charges to the negative charges. I'm just going to show 3 arrows here. I'm going to maybe get carried away. Okay, so that's the electric field. And there's a voltage associated with it. So across the plate, there's a change in voltage, delta V. This is a higher voltage. This is a lower voltage. Okay, so what do we know about parallel plate capacitors? Well, there's an equation that gives you the capacitance based upon the dimensions of the capacitor. So it doesn't depend. The capacitance doesn't depend upon the voltage applied to it or the charge on the capacitor. It only has to do with this formula. The capacitance is equal to epsilon 0 times the area divided by the distance. So this is a constant which is in your book, and I'll find it here in just a second. Epsilon 0, it's just our Coulomb's constant with a couple of factors involved. So it's 8.85 times 10 to the minus 12th Coulomb squared per Newton meter squared. So that's a constant. And the area, so the bigger you make the area, the more area the plates have, the higher the capacitance is. Because the capacitance is a measure of how much charge you can store across this capacitor. So the larger the area, more charge. And the smaller the distance, what happens there is you also can have more charge, and therefore, so the closer these plates are, the higher the capacitance, and the larger the area, the larger the capacitance. So for part A, which is just asking for the capacitance, we just have to plug into that equation. So if we look at the problem statement, it gives us the area. It says the area is 2.3 centimeters squared. Now it's in centimeters, so we have to convert to meters. So to convert centimeters to meters, you divide centimeters by 100. So to convert centimeters squared to meters squared, you divide by 100 squared. So we take 2.3 divided by 100 squared, and that would give us square meters. It's going to be a fairly small number, 2.3 divided by 100 squared, 2.3 times 10 to the minus 4 meters squared. Okay, our distance is given in millimeters, I think, 1.5 millimeters. So to convert from millimeters to meters, we divide by 1,000. So 1.5 divided by 1,000 is 0.0015 meters. So we have everything, we just need to plug it into the formula. The capacitance is 8.85 times 10 to the minus 12th. That's Coulomb squared per meter, Newton meter squared, multiplied by the area, which is 2.3 times 10 to the negative 4 meters squared. And we divide that whole thing by the diameter, the distance between the plates, 0.0015 meters. So 8.85 e to the negative 12 times 2.3 e to the negative 4 divided by 0.0015, and I get 1.36 times 10 to the minus 12th. And the capacitance, the units of capacitance, I'm trying to remember what those are. Well, actually, capacitance is also Q divided by V. Q is the charge in coulombs, and V is the voltage. So if you work all the units out, it'll end up being coulombs per volt. So that's the units for capacitance. And that's called a farad. So it's a coulomb per volt is a farad, just another definition, so we don't have to say coulombs per volt. So this is a farad. We use F for that. Okay, so that's the capacitance of the capacitor. Okay, so the next thing we do is they're asking for is what is the charge on the capacitor? Well, we're given the voltage applied to this is 12 volts. And the relationship between voltage, charge, and capacitance we just wrote on the previous page. So if we solve for charge, Q, that's equal to the capacitance times the voltage. So that should be easy enough. So the capacitance was 1.36 times 10 to the minus 12 farads multiplied by 12 volts. And a farad is a coulomb per volt, so if we multiply coulombs per volt by volt, we get coulombs. 1.36 e to the negative 12 times 12. So we get 1.63 times 10 to the minus 11th coulombs. And what this is that we transfer enough electrons so that there's 1.63 times 10 to the minus negative charge on this one of 1.63 times 10 to the minus 11th, and we have a positive charge on this plate of 1.63 times 10 to the minus 11th coulomb. So it's the charge on each plate. So that's B. And then the final one is the electric field. And so we had a relationship between voltage and electric field earlier on in the book, and it was equal to, I'm trying to find it. So it's coming to me here. So we had voltage was equal to the electric field times the distance. That was the one that V is Ed. So in this case, D is the distance between the plates. The voltage is 12 volts. And so we can solve for the electric field. It's just going to be equal to the voltage divided by the distance. And so the voltage was 12 volts. The distance was 0.0015 meters. So we get 12 divided by 0.0015. So we get 8,000, and it's volts per meter, or it could also be 8,000. And electric field was also charge per, it was also force per unit charge, so it would also be newtons per coulomb. So either one of those would be true. So let me go and check the answer book and make sure that I have the right answers. Okay, so I've checked the answers, and these are correct. The only thing I'd like to add is that 10 to the minus 12 is the prefix is called pico, so this would be 1.36 picofarads. Likewise, this would be equal to 16.3 picocoulombs. Pretty sure that's right. Yes, because that would be 1.63 times 10 to the minus 11th is the same as 16.3 times 10 to the minus 12th. So we could do that. So that would be another way of writing those two particular quantities, but otherwise everything is correct. This is problem, I forgot which one it was, problem 33 on page 567. It's a very short problem, both in length of discussion and in how to do it. It's pretty easy. It says, given a 2.5 microfarad capacitor and a 6.25 microfarad capacitor and a 6-volt battery, find the charge on each capacitor if you connect them in series across the battery and in parallel across the battery. So let's just draw a diagram. So we represent a capacitor as this in circuit notation. And when we have them in series, they're connected one end to the other, like this. So this is a series connection of two capacitors. This is a wire. We would go to a battery. And so there's a voltage across this battery, which then will be across the two capacitors. And so let's call this, let's say this capacitor is the 2.5 microfarad capacitor, and this is the 6.25 microfarad capacitor. Okay, so we know the total voltage across this thing is going to be equal to, from here to here, what's the total voltage? It's given as 6 volts. So we have 6.0 volts voltage. So we'll get some voltage drop across here and some voltage change across there. And it depends upon the capacitance. And the way it works is we have the same charge. So what we'll have is we'll have, this will be, say, the plus side. And this will be the negative side. And this will be the plus side. This will be the negative side. So what will happen is the electrons will go around here through the battery up to here, and then we get excess electrons. And because we have electrons here, the electrons here will be pushed over to the other plate. So there's no flow current through the capacitor. It's just shifting electrons from here all the way around there, and then the ones from here to there create the charges on the capacitors. And what we know is that, at least let's call this C1 and this C2, we know that the charges on each one of these capacitors has to be the same, because what comes around here has to go there, so they're equal to each other. So we know that Q1 is equal to Q2 as far as the charge. We also know the total voltage is going to be equal to 6 volts. So if we look at the relationship between capacitance and charge and voltage, we have this. So C1 is Q1 over V1, and C2 is equal to Q2 over V2. Okay, now we also know that V1 plus V2 has to be equal to 6 volts. I have to get that. We know the two capacitances. We know that these two charges are equal to each other. So we have enough equations. We have as many equations as unknowns. Our unknowns are what are the two voltage drops across the two capacitors and what are the two charges. And we have 4 equations. So 4 equations of 4 unknowns. And the question is, how do we solve for this? What do we do? And so we need to be able to rewrite these equations in one unknown. And so let's just think about this. How would we do that? Well, I think if we solve for the Q's and set them equal to each other, so let's do that. So Q1 is equal to C1 V1, and Q2 is equal to C2 V2. Okay, now we know the charges are the same, so we know that C1 V1 is equal to C2 V2. And let's add another page on. So now we have, this is one equation with 2 unknowns, but we have another equation with the same 2 unknowns. So we can use substitution if we want to. So let's say C1 V1 is equal to C2, but V2 is equal to 6 minus V1. So we could, for V2, we can put in 6 minus V1. So we can algebraically solve for V1 now. So what we'll do is we'll multiply it out. So we get 6C2 minus V1 times C2, and then we'll add this to both sides. So you'll get C1 V1 plus C2 V1 is equal to 6 C2. You factor out V1, so you get V1 is C1 plus C2 is equal to 6 times C2, and then we can solve for V1. So V1 is equal to 6 times C2 divided by C1 plus C2. Okay, let's go to the next page, and so let's plug in the numbers, and we'll find out C2 and C1. So C1 was 2.5 microfarads, and the other one was 6.25. So we're going to have 6 times 6.25 divided by the sum of the other two. Right? Okay. So we'll have 2.5 plus 6.25. So this is voltage. These are all capacitances. So the capacitances cancel out. So 6 times 6.25 divided by 2.5 plus 6.25. And we get 4.3 volts. Okay, and therefore V2, by going down here, is just 6 minus 4.3. So that's 1.7 volts. So those are the voltages. Now we can use these equations, or actually these equations here, to find the charge. So the charge on capacitor 1 is going to be C1, which is 2.5 times 10 to the micros, minus 6 farads, times the voltage, which is 4.3 volts. So 2.5 e to the minus 6 times 4.3 gives you 1.08 times 10 to the minus 5 coulombs. And Q2 is equal to 6.25 times 10 to the minus 6 farads times 1.7 volts. 6.25 times 10 to the minus 6 times 1.7 is, well, actually it should be the same, and it does come out to be the same. It's 1.7, so it's pretty close. It should be exactly the same, because we said that Q1 equals Q2, so this is just rounding off error. So the charges are the same, and that makes sense. Okay, so that's part A. So what we did again was we said that the charge on each capacitor had to be the same. We knew the total voltage had to be 6 volts. So we had V1 plus V2 is 6 volts. And we also knew that the voltage and charge are related by the definition of capacitance. Capacitance is equal to charge over voltage. So we solve for charge in these two equations, and then we set them equal to each other. And then we use substitution, use this equation to substitute in, so that instead of having V2 and V1 unknown, we just had V1 unknown. We algebraically solve for V1. So we ended up with that result. And then we plug the numbers in, 6 volts times 6.25 microfarads divided by 2.5 plus 6.25 microfarads. Microfarads cancel out. We get 4.3 volts for V1 across here. And then 6 minus 4.3 gave us the remaining voltage drop, 1.7 volts. So those are the voltages and the charges. We calculated them out. And we really only needed to calculate one because we made the assumption that the charges on the capacitors would be the same. Okay, so that's part A. So it's actually taking a little longer than I thought it would, but then it says in parallel. So what in parallel means is you have this like that. those are in parallel, and they come down here to the battery. And so this is 6 volts, and the difference in parallel, we have the same voltage drop across. So we know V1 is equal to 6 volts, and we know that V2 is equal to 6 volts. So let's write down what we know. We know that the capacitance of capacitor 1 is going to be the charge divided by the voltage, Q1, V1. So Q1 is just going to be equal to C1, V1. And we already know what these both are. So Q1 is going to be equal to C1, which is was the 2.5 microfarads. So we take 2.50 times 10 to the minus 6 microfarads, and we multiply by the voltage, which is 6 volts. And so we get 2.5 e to the minus 6 times 6. 1.5 times 10 to the minus 5 coulombs. And likewise, Q2 has the same relationship between voltage, capacitance, and charge. So V1 is equal to V2. The capacitance changes to 6.25 times 10 to the minus 6. And I shouldn't have a micro in there. I should just have farads. Sorry about that. Farads times 6 volts. So since this one has a larger capacitance than this one, we would expect that the charge is also greater. So we get 6.25 e to the minus 6 times 6 is 3.75 times 10 to the minus 5 coulombs. So those are the charges. In the first problem, the charges were the same, and the second part of the problem, the voltages are the same. The second part of the problem is a lot easier than the first, obviously. So I'm going to just take a second here, check the answers. Okay, so I'm looking for the answers, and everything's correct except right down here. I should have I left a 0 out, so we'll just put that in there. Make sure we'll just make them the same. 1.08. Another way of writing this would be 10.8 times 10 to the minus 6 coulombs, which 10 to the minus 6 is a microcoulomb. So that would be one way of writing that, as well as over here, we could rewrite this as 15 microcoulombs, and this could be 37.5 microcoulombs. We'd multiply by 10 to get 15, 10 to the minus 6. 10 to the minus 6 is microcoulombs. This is problem 34 in chapter 16. And we're just asked to find equivalent capacitances of two capacitors. Here on the left-hand side, we have them shown in series. On the right-hand side, we have them shown in parallel. And the key thing to remember about series capacitors is that the charge is the thing that is kind of a common thread. So if one capacitor has a plus charge, the other plate has to have a minus charge, and the corresponding capacitor that's in series has to match up, because the electrons that are on this plate go over to this plate to make this one negatively charged and make this one positively charged. So they have to balance up. There's no current that flows between these capacitor plates. So any electrons that are on in this side are just redistributed from one plate to another. Now over here we have voltage across the two capacitors, and because these are connected by a wire, the voltage here is the same as the voltage there, and the voltage there is the same as the voltage there. So the common thing here is that we have the same voltage across each capacitor. Here we have the same charge across each capacitor. And if you apply that to the definition of capacitance, we find out that for series capacitors, that the equivalent capacitance is just the reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of the individual capacitances. So in this case, we would have that the equivalent capacitance of the two capacitors in series, we take 1 over those. And I'm just going to include the numbers and then put the microfarads in at the end, as long as they're of the same order. You know, if they're picofarads or nanofarads or whatever they are, you don't have to carry all that through until the end. So what we'd have is we would have 1 divided by 4.2 plus 1 divided by 8.5. So we get 1 over the equivalent capacitance is equal to 0.356, and therefore the equivalent capacitance is going to be equal to 1 over 0.356, and we get 2.8 microfarads. Every time you have two capacitors in series, the equivalent capacitance is always less than either one of the original capacitances. And so we get 2.8 microfarads, which is less than 4.2 and also less than 8.5. Okay, now when you do it in parallel, what we find out, it's very simple. The equivalent capacitance is just the sum of the two capacitances. And so our equivalent capacitance in this case is 4.2 microfarads plus 8.5 microfarads. And we just add these two together and keep the micro. So 4.2 plus 8.5 is going to be 12.7. So we'll get 12.7 microfarads. And for parallel capacitors, the equivalent capacitance is always greater than the individual capacitances because we're adding them together, obviously. So you get 12.7. This is the one that, you know, you sometimes think that, oh, I should always add stuff. But in this case, the total capacitance is less than the individual capacitances. This is problem 37, chapter 16. And what we have here, let's see, read what it says. For the system of capacitors shown in the figure, find the equivalent capacitance of the system, the charge on each capacitor, and the potential difference across each capacitor. So the procedure is that you're going to combine these two capacitors, which are in series together, to create one capacitor. We'll combine these two together into one capacitor. That'll leave us two capacitors in parallel, which then we can combine into a single capacitor. And with that capacitor, we can calculate the amount of charge that's going to be on each one of these right here and right here. So we'll replace these four capacitors with a single capacitor. And then we also know the voltage drop across the equivalent capacitor. And you kind of have to go backwards. So we'll start with this. We'll go to an equivalent capacitance. We'll figure out the total charge, and then we'll kind of go back to two parallel capacitances, and then we'll go back to four capacitors. So it's a fairly complicated problem. So the first step is again to combine these into equivalent capacitances. So the first thing we're going to do, we're just going to look at the capacitors first, and we want to make this circuit. So we're going to replace these two series capacitors with one capacitor. And we're going to replace that. So you've got to use the equation for series capacitances. So let's call this Q equivalent 1, and we'll call this Q equivalent 2. So Q equivalent 1, because they're in series, we have to use the reciprocal relationship. So let me move this down a little bit. Maybe I can get them both here. Okay, so we take 1 over 3, and again, everything's microfarads, so we're just going to take 1 over 3 plus 1 over 6. And what that'll give us is 1/3 plus 1/6 is 1/2. And if you take the reciprocal, we find out the equivalent capacitance of 1 is 2 microfarads. Okay, let's go ahead and do the second one. So 1 over the equivalent capacitance associated with the lower two are going to be 1 over 2 plus 1 over 4, which is 1/2 plus 1/4 is 3/4. And therefore, the equivalent capacitance is going to be 4 divided by 3, which is going to be 1.33 microfarads. So we can write that up here. This would be 2 microfarads, and this equivalent capacitance would be 1.33 microfarads. So now we have 2 capacitors in parallel, and when they're in parallel, we just add them. So our total equivalent capacitance is just going to be equal to the equivalent capacitance 1 plus the equivalent capacitance 2, and we have those. We have a 2 and 1.33, so it's 2 microfarads plus 1.33 microfarads, which is going to be 3.33 microfarads. So that's the answer for part A. What is the equivalent capacitance of the system? Okay, I'm just going to pause for just a second. Okay, I was just checking to make sure everything was okay before I moved forward. So it was correct. Okay, now the second part says find the charge on each capacitor. Well, if we go back to right here, this drawing, what we'll have is we'll have this side of the capacitor will have plus 90 volts, and here we'll have 0 volts. So the difference is going to be 90. We're going to have a drop of 90 volts. We'll have an increase in the battery of 90 volts, and we have a drop of 90 volts in the capacitor, so that it's a circuit. The total voltage around the circuit has to be 0. Okay, so what we're going to do is we're going to look at, but because these are parallel, you have the same total voltage across this part of the circuit as this part of the circuit because they're connected. So the voltage here has to be the same as the voltage there, and the voltage at this point has to be the same as the voltage there. So what we can say is that the amount of charge that's on this plate, which would be the same as the charge on this side of this plate, is going to be, we can just get it from the definition of the capacitances. So the equivalent capacitance for these two combined into one is going to be equal to the charge this is charge for, let's call it the equivalent part 1 divided by V1. And so what we have to do is we can solve for Q1. Q1 is just equal to the equivalent capacitance of these 2 capacitors times the voltage. And so the equivalent capacitance is 2 microfarads, and we multiply by 90 volts. And so 90 times 2 is 180, so we get 180. Farads times volts is coulombs because we have charge, so we have 180 microcoulombs. So that's the charge that's going to be here. We'll call that Q1. So we have plus Q1 here, we have minus Q1 there. Okay, the second thing is we'll do the same thing with the other equivalent capacitances. So Q equivalent 2 is equal to Q2 divided by, again, the voltage is the same because we have 90 volts across those. So if we want to solve for Q2, it's going to be equal to C equivalent 2 times V I probably should just use V instead of V1. Let me erase those. And so we have an equivalent capacitance of 1.33 microfarads times 90 volts. And if you take 90 times 1.33, 1.33, you get 120. So we'll have 120 microcoulombs. Let's call that, make sure we put the Q right here. Okay, so down here we have plus Q2 and we have minus Q2. Now the thing about capacitor charges is when we have capacitors in series, you get the same charge on all these. So what's going to happen is we'll have plus Q2 here, minus Q2 there, plus Q2 there, minus Q2 there. So when we look at this equivalent capacitance, all we're seeing is plus Q2 and minus Q2. The internal stuff doesn't show up. But when we have series capacitors, this charge, the negative charges go from this plate to that plate, leaving the positively charged internal plate. And you can do the same thing up here. This will be Q plus Q1. On this plate will be minus Q1. On this plate will be plus Q2. And on this plate will be minus, I messed up there. Hold on just a second. This should be, let's get a smaller eraser here. This should be Q. These all should be Q1s. So that's plus Q1. This is minus Q1. Okay, so those are the charges on all the plates. We'll have plus 120 microcoulombs, minus 120 microcoulombs, plus 120 microcoulombs, minus 120 microcoulombs. Here we'll have plus 180, minus 180, plus 180, minus 180. So we know the charges on each capacitor now. The final one is what is the voltage drop across each one. So we go, now that we know the charge and we know the individual capacitances, here we use the equivalent capacitance, but now when we break it up further, we use the capacitance of each capacitor. So I'm going to insert a page right here. And what we knew was that Q1 was equal to, what was it equal to? 180 micro, so it's 180 microcoulombs. Q2 was equal to 120 microcoulombs. So we apply the definition of the capacitance to each one of these using these charges. So if you're looking at the 3 microfarad capacitor for that particular case, so the capacitance, which is 3 microfarads, keep getting my thing screwed up here, is equal to, we use, this is Q1 with the 3 microfarad capacitor, so we use 180 microcoulombs, and we divide by the voltage. That's our unknown now. So our voltage associated across the 3 microfarad capacitor is just going to be 180 microcoulombs divided by 3.00 microfarads. The micros cancel out, and 180 divided by 3 is 60, so we get 60 volts. And it has to be somewhere between 0 and 90. It can't be more than 90. So it works out, makes sense. Now let's look at the second one, the 6 microfarad capacitor. So the same thing, the capacitance is 6 microfarads. It has a charge of still 180 microcoulombs, because that's what happens with the capacitors in series, divided by the voltage. For the, we'll just leave the subscript off now, but if we put the 6 microfarad capacitor, it's just going to be equal to 180 microcoulombs divided by 6 microfarads, and 180 divided by 6 is 30. So we get 30 volts, and lo and behold, 60 plus 30 is our total voltage, which is 90. That's how it has to work out. Okay, so that's those 2 capacitors. Then we go to the 2 microfarad capacitor. What's happening there? Well, of course, the capacitance is 2 microfarads. We're trying to figure out what the voltage is. The charge is down here. The charge is, or was it up here? Charge here. Q2 was 120. Here we used 180. So we'll have 120 microcoulombs divided by the voltage. Capacitance is charge divided by voltage. So we've solved for the voltage. It's 120 microcoulombs divided by 2 microfarads. 120 divided by 2 is 60. So it's 60 volts. And then if we look at the last capacitance, which is this 4 microfarad capacitor, we get 4 microfarads is equal to, again, 120 microcoulombs, which is the charge. Remember, we have the same charge. We just have plus and minuses, divided by the voltage. If you solve for the voltage, we get 120 microcoulombs divided by 4.00 microfarads. 120 divided by 4 is 30 volts. Again, 60 plus 30 equals 90. And you can kind of see what's happening here is, this capacitance is twice that capacitance. This capacitance is twice that capacitance. So because of that, you get the same voltage ratio here, 60, 30, 60, 30. Because these capacitors are which one has the most charge? Well, let's go back. So the most charge is the one with the higher capacitors, the higher value capacitor. 6 plus 3 is 9. So there's more capacitance there. And so more gets stuck on that end than this end. So that's how it works. Let's kind of explain it again, because it is fairly complicated. So we have our original circuit. We take these 2 capacitors and these 2 capacitors separately, and we use the property of capacitors in series, which says you add the reciprocals, and that's the reciprocal equivalent capacitance. So we replace these 2 series capacitors with 1 capacitor. If we go down here, you can see 1 over 3 plus 1 over 6 is equal to 1/2, and the reciprocal of 1/2 is 2. So we can replace these 2 capacitors with 1 capacitor at 2 microfarads, which is less than each one of these individually. And you can do the same thing for these 2. And you get 1.33 microfarads for the equivalent capacitance. These are now in parallel, and when you have parallel capacitors, you just add them, which was actually in the next page here. So to get the total equivalent capacitance, we have the 2 in parallel equivalent capacitances, and we get 3.33 microfarads. To find out how much charge is on each one of those capacitors, we look at the original circuit, and let me just move this back up here so we can look at these first 2 pages. So here we have the equivalent capacitance, and we have a 90-volt drop across each capacitor because of the way these circuits are set up. So we know the voltage drop, and we know the equivalent capacitance. So we use that, again, the definition of capacitance, to solve for the charges. And so we get Q1 and Q2, 180 microcoulombs, 120 microcoulombs. And so we know the charge on this plate is 180. This is minus 180. This is plus 120. This is minus 120. And when we expand this out, the charge still has to be the same here. It still has to be plus 180, and over here it has to be minus 180. But because the charge just moves from one plate to another, we have to just have the equivalent on either side. So if this is minus 180, this is plus 180, this is minus 180, this is plus 180. And you can just do the same thing with the lower branch. Okay, so now once we know the charges on these capacitors, then we can look at them individually. Knowing the capacitance and the charge, we can calculate the voltage. So that was the last step that we did. Let's move this back up here. So now we're back to this figure. And we know the charge is on the capacitor. and we now know the original capacitances. So we solve for the voltage, and we get a 60-volt drop across this capacitor, and we get a 30-volt drop across this capacitor. 60 plus 30 has to equal the total drop, which is 90. And you can do the same thing on the lower leg of this circuit. 60 voltage drop, 30 voltage drop, the total is 90 volts, which is what's across the battery. Okay, so that's how that works. This is problem 49, chapter 16. Let's just read the problem. It's on page 568. The voltage across an air-filled parallel plate capacitor is measured to be 85 volts. When a dielectric is inserted and completely fills the space between the plates, as in figure 1624, the voltage drops to 25 volts. What is the dielectric constant of the inserted material? Can you identify the dielectric? B, if the dielectric doesn't completely fill the space between the plates, what could you conclude about the voltage across the plates? So I've got a drawing here with the two plates, and this is the dielectric material. And I'm sticking in there. When I put the dielectric material in, what happens is the voltage changes to 25 volts. And the definition of capacitance with a dielectric is you have your dielectric constant times your capacitance with a vacuum between the plates. So what happens is the capacitance increases. And because when we start out, there's a certain amount of charge on the plates. So you got a certain number of electrons on this side and a certain number of ions that don't have electrons on this side. And during that period of time, with the original capacitance, we know the original capacitance is equal to the charge originally divided by the voltage. So what happens is, because this is not hooked up to a battery, then the charge is not going to change. And so when the capacitance changes, the voltage changes, and the voltage goes down as you put the dielectric material in there. If you hooked a battery up to it, then you could put additional electrons on this side and take additional electrons from the positive side. And therefore, you could get back to 85 volts, which then would mean there would be more charge. So in this case, we have a certain amount of charge, which is fixed, and then we put the dielectric material in, and the voltage drops. So in this case, the difference in the voltage is also related to the difference in the capacitance. So we could say that V was equal to, it actually goes the opposite direction here, because the capacitance actually goes up. The dielectric constant for materials is greater than 1. So as the charge goes down, so in this case what we would say is that the new voltage would be equal to the old voltage divided by the dielectric constant. So we can actually figure out the dielectric constant directly from that. So it's just going to be equal to V divided by V0. I just realized I did it wrong when that worked out. So actually, because what's going to happen is the voltage is going to go down. And so what we'll have is that, what will we have? We know this is going down. We know the dielectric constant is greater than 1. So it's going to be that V0 is equal to the dielectric constant times the new voltage, because that's going to be 25 and that's going to be 85. And if we divide 85 by 25, then we'll be in shape. So K is actually equal to V0 over V, which in this case will be 85 volts divided by 25 volts. So our dielectric constant in this case is 85 divided by 25, which is 3.4. So that's the answer for part A. This says, can you identify the dielectric? So we'll go into the book, and it's going to be near the end of the chapter. And table 16.1, which is on page 558, dielectric constants for various materials at room temperature, and we see that the one material that has a dielectric constant of 3.4 is nylon. So we're going to assume the material is nylon. And then the question was, the third question, well, if the dielectric doesn't completely fill the space between the plates, what could you conclude about the voltage across the plates? Well, of course, if this is going to be your maximum voltage for a given charge, if we completely fill the plate, the charge completely fill the space between the two plates, the voltage is 25. Therefore, if we don't completely fill the gap, then we're going to have a voltage somewhere between 25 and 85, depending upon the percentage. So the answer to part B is that the voltage will be between 25 and 85, depending upon the percent that's filled. And let's just stop for a second. So just check the answers and we're okay. So it's fairly just more of a qualitative type problem. But you kind of have to remember about dielectric constants. If you have a fixed charge on the plates and you put a dielectric material in, what that's going to do to the charge remains the same because there's no place for the charge to go. The dielectric material will cause, there will be polarization of the molecules within the dielectric material, which will create an opposing electric field, and therefore the electric field is less. And because the electric field is less, the voltage has to be less. So that's, and also if we know that the dielectric material, the dielectric constant of the material is always greater than 1. So when I wasn't exactly sure what ratio I should use when the charge was constant, I did it just kind of a ball, order magnitude, or just sort of a guess of which way it would go. Knowing which way it goes, not really a guess. I knew which way it would go, and so I knew that there would be ratios. And I knew that the ratio had to be the dielectric constant, which originally is the ratio of capacitances. When you look at the voltages, I knew that they had to result in a positive or greater than 1 value for the dielectric constant. So I knew which way these things had to go just from kind of using deductive reasoning.